Hi everyone, myself Dr. Akshay, working as Assistant Professor in Department of Electronics and Instrumentation Engineering at VJEC Hyderabad. So today we are going to discuss about mathematical modeling of physical processes under Process Control Instrumentation course. We'll see what is the purpose of having mathematical modeling. So basically, if we have a mathematical model is going to give us cause and effect relationship. It is going to give us the relationship between input and output, we can say in another way. So basically, if we have a mathematical model which represents basically that entire process mathematically, so if we have a mathematical model, we can understand the process that we need to control. Once we understand what type of process we are going to handle, that is nothing but what are the various parameters, what are the various process elements of that particular we can say the process, then we can design good controllers. That is nothing but we can optimize the process design, and we can maintain the output at a desired set point or at desired level. So once we have a plant, once we understand the nature of the plant, say whether it is a linear, it is a non-linear, once we have a model, we can relate input with output and other plant parameters. So we can use it to design a control strategy. So whether I should go with P controller, PID, right? In addition to that one, let's say once I have a mathematical model, I can use it for simulation purpose, and through simulation studies we can understand the plant behavior. We can use this simulation technique to train the operators. We can understand what is the plant behavior under different operating conditions by applying various input or stimulus like standard test signals, ramp, parabolic, step inputs. So in addition to that, once we have a model, so what we can do, we know machine learning concept. So basically in machine learning concept, once we have a model of a process, so for example, say I need to do health monitoring, or let's say I need to do disease diagnosis or early disease prediction. So if I have a model, right, then what I can do, I can estimate or I can predict or I can know whether someone is suffering with a particular disease, or what is the level of that particular disease, or can I prevent that disease by detecting the early symptoms or early signs. So we know that if we have a model, we can predict or we can estimate it. So similarly, here in process control instrumentation also, if we have a model of a process, that model will help us to understand the behavior of that particular plant. So similarly, we have some advanced control schemes or model based controller approaches like internal model controllers, or we have model predictive controllers. So like MPC, IMC, these types of MBCs we can design if we have a good model. So we can say it model based control. So that we can use it to minimize effect of disturbance over a process. Also, not only that, we can also do a good set point tracking, right, so that we can maintain output at the set point variable. So this is going to give us a better process economics. Thereby we can reach or we can meet one of the objective, that is a profit. So coming to the mathematical model of the process, so we'll see one example how we can find a mathematical model for a process. So here, for example, we are considering one example. This is a liquid level process. This liquid level process is one of the first order process. So we'll consider this liquid level process to understand how to get a model or mathematical model for a given we can say the plant or for a process. So if we consider we are using here a liquid level process, and here water the tank we are using, it is a cylindrical water tank is there. So let's say our aim is to find, so I need to find here a mathematical model for my tank for the given, let's say, cylindrical tank. Now first thing, why I should have a mathematical model? As we discussed earlier, now for example, say if I have a mathematical model, right? So what can I do? I need to know that at how much time is required to get, let's say, 50% water in this particular tank, or I need to know at what time t, right, or at what time t water level will be 50%, or I need to know that after say 10 seconds how much will be the water level. So let's say I need to know these things. So for that purpose, if we have a mathematical model, then we can easily analyze plant behavior. So we'll see how to find mathematical model for this particular cylindrical liquid level tank. So basically, when we are using mathematical modeling, or when we have to find out mathematical modeling, we are using various first principles or fundamental laws. So in this particular case, we are using a principle called as, or we can say the law of conservation of mass, right? So, or I will call it as a mass balance principle. So what exactly this mass balance principle is there, and how I'm going to use this mass balance principle in this particular application. So you can just consider in a simple way. So how, let's say I'm going to add some water in this. So where the water will go? So what are the water I'm going to add or pour in this particular tank? Some let's say I'm going to pour 5 liter water in this particular tank. So if 2 liter water is went outside the tank, say when I'm pouring say 5 liter, so remaining 3 liter water will be stored in this particular tank. So I can say that 3 plus 2. So how much is the water accumulated in the tank? How much water left out of the tank? And what is the total water poured in the tank? So that is a 5. So simply in a similar way, what we can do, we can consider the total input mass. We need to consider the mass principle, that is nothing but law of conservation of mass. So total input mass in, or the input mass with respect to time t, where the let's say some water I'm pouring in this particular tank, where the water will go, some water will be stored in the tank and remaining water will go out from the tank. So we can say the total input mass with respect to time t, that will be equal to accumulation of mass, which is nothing but water stored in the tank with respect to time t, and the remaining water will leave the tank. So that is nothing but we can say the output mass, or we can say even output flow rate, we can say, or the total water which has, or the water which has left from the tank, we can consider. So in a simple way, we can say input flow or inflow minus, if we rewrite the equation, outflow is equal to accumulation of mass. So here accumulation of mass is nothing but how much is the water stored in the tank. Inflow, let's say I will consider in this particular case, say F in, this is the input flow coming into the tank. So here I will show on the diagram F in. Let's say the water which is going out from the tank, that nothing but we are showing here as a outflow. So let's say that I will represent here with a F naught. Consider the area of the tank is A. Let's say the water stored in the tank till height h we can consider. So I will rewrite the parameters. Let's say F in is nothing but it is the inflow rate. We can consider it is a volumetric flow rate also. Then this may be cubic meter per second we can consider. Then FO, this is the outflow rate, that is nothing but water which is going out from the tank. This is also cubic meter per second. Let's say area of the tank. So consider area of the tank. This is a cylindrical tank, so it is a pi by 4 d square. Let's say this we are considering in terms of meter square. let's say h, this is nothing but height of the water, or in a simple way we can say water level in the tank. This is also, let's say, in terms of meters. So let's say these are some parameters. Now you can see, we'll go to the we can see here, through a pipe water is coming into the tank with the flow rate F in. Through a pipe water is going out from the tank having a flow rate F naught. This water is passing through a wall. So let's say this is a wall, and let's say R is the resistance to the flow, right? So there is nothing but, say, if wall is fully closed, no water will go out from the tank. Let's say it is a open, means there is nothing but this R will decide how much water will pass through this particular pipe, right? So let's say these are the parameters for this particular tank. Now our aim is to find out mathematical model for the given process tank, which is a cylindrical tank. We'll be using this mass balance principle to find out the equation or transfer function model for this case. So let's say this is our equation A. This is nothing but input flow minus output flow is equal to accumulation of mass. So I will rewrite the equation A in terms of these parameters. So Fi is the input flow minus F naught is the output flow is equal to accumulation of mass. Accumulation of mass, it depends on you can say the area of the tank, and we can say it is a d Ah by dt. As area is constant, we can rewrite it as a into dH by dt. So this is input flow minus output flow is equal to accumulation of mass. So let's say this is equation B. Now if you see this particular tank, right? So you consider the water stored in the tank. I will consider it like a electrical equivalent voltage of a circuit, right, or potential difference, right? I can consider here flow rate like electric current I. I will consider wall resistance which is shown here as a R, like electric resistance of a circuit. Now if you apply Ohm's law, that is V equal to IR. Here in a similar way I can write liquid store accumulation of water in a tank, H is equal to flow rate F naught and wall resistance R. So we can rewrite the equation for F naught as H by R. So let's say this is equation C. Now we'll rewrite equation B, that is nothing but input flow Fi minus F naught is equal to area A into dH by dt. Here we'll substitute the value of F naught, that is output flow, which is represented by H by R, A into dH by dt. So let's say this is our equation, right? So this is, let's say, our equation C, or the next equation. Now I will rewrite the equation by multiplying R, so that we will be getting a time constant element. So I am going to multiply this entire equation C by R. So I will be getting equation R into Fi minus H is equal to R into A into dH by dt, right? Now as we need to get a transfer function model, basically we know the transfer function model definition. It is nothing but it is a Laplace transform of output response divided by Laplace transform of input response by considering all initial conditions are 0. So to find out that one, let's say I am having this equation D, I will apply Laplace transform to this entire equation D. So I will be getting here equation R into Fi of S minus H of S is equal to S into Ra into H of S. So I will rearrange this equation E. So R into Fi of S is equal to, I am taking H of S common, and after rearranging it I will get 1 plus S into Ra. Now as we know, our aim is to maintain water level inside this particular tank. So the output for this particular tank is water level or accumulation of water, H of S. The input is the flow rate, that is input flow rate Fi is equal to R divided by S into Ra plus 1. Now we know that let's say time constant of this particular tank, as this is a first order system, so let's say tau is the time constant which is given by Ra. So we can rewrite this equation as H of S divided by Fi is equal to R divided by tau S plus 1. So this gives us this equation F. This gives us a transfer function model of a cylindrical water tank or cylindrical liquid tank we can consider, right? So now once I have this transfer function model, what I can understand from this model? Now if you consider this equation F, now from the equation F, so if I consider here the equation F, from the equation F we will try to understand if we have a mathematical model, what we can understand or how we can understand about this particular process. So now if I know the value of R, let's say I have value of R as well as tau. If these two are known, then I can say that I know the mathematical model for my particular tank. So how we can find out this particular parameters like R as well as a tau? So if we conduct experiment and if you note down the liquid level, say I will conduct an experiment that is time, and with respect to time t, let's say I'm going to measure water level in the tank. So let's say we'll start let's say one experimentation, and in that let's say we'll try to find out how the water level changes with respect to time t, and say we got some readings. We'll note down the reading till we'll get a steady state. So for example, from the obtained readings, let's say we got a graph. So with respect to time t, let's say we'll plot h of t, and we'll find out these readings we are taking till we are going to get steady state. So let's say I got steady state at let's say 3 meters. So we'll note down, we'll plot the values, and from that we'll get the graphs. Let's say I got this particular response for the given tank, and as we know that the time required for first order system to reach it's a 63.2% of steady state or the final steady state. Let's say this is a steady state response. So I will be finding out say 632. So at what time it reaches the 63.2%. So let's say that is a tau value. So once we got tau experimentally, right, say already we know the area of the tank, say pi by 4 d square. Say as we know d, let's say it is a known one, so we can say we know a, right, we got experimentally tau value. Then as we know tau equal to RC, we can find out value of R, that is tau divided by C. So once we get the value of R tau, we can say that yes, we know the mathematical model, or we got a mathematical model of this particular tank. Now what advantage I will get if I have a mathematical model of this particular tank? So we'll see it next. So now as we got the mathematical model, that is in terms of transfer function model for this particular tank, that is h of s divided by fi of s is equal to R divided by tau s plus 1, where we got tau is equal to R into E. So now let's say experimentally we got the values of say tau is known to us, R is known to us, right? So for example, I will write it here, say R is equal to, say I got 2, let's say tau I got something in terms of say 5 minutes for example, right? So I got this transfer function model h of s divided by fi of s, this is equal to 2 divided by 5s plus 1. Let's say this is the model that we got for my process tank. Right now, how can I use this to understand the plant behavior? I need to know how the water level will changes with respect to time t, or I want to know that at a particular time t how much will be the water level in the tank. So let's say I need to find out this. So consider this is the known equation. Let's say I'm going to consider this as a equation f, for example. Now I will apply a step input. Let's say as I told that through simulation studies we can understand the plant behavior if we have a good plant model. So let's say this is a plant model available with me, and let's say I'm going to apply a standard test input. So in this case, let's say I'm going to consider I'm changing the control wall, right? There is nothing but suddenly I'm going to change the input flow rate, right? So let's say I'm going to apply here a unit step input, consider 1 by s. So I'm applying here a standard test signal, that is a unit step input 1 by s. So this equation f becomes h of s is equal to 2 divided by 5s plus 1 into 1 by s, right? So this fi of s is a value is 1 by s. So once we take say partial fraction and later we'll apply inverse Laplace transform, as we need to know how the water level is changing with respect to time t. So we are going to apply here inverse Laplace transform. So we can write the equation, right, in terms of change in water level with respect to time t after taking inverse Laplace transform. So we will get here, let's say h of t is equal to h naught. This is the initial liquid level in the tank, plus let's say for example I'm taking this equation. Let's say h naught is the initial liquid level in the tank or water level in the tank, plus 2 in bracket I will be getting 1 plus e to the power minus t by tau. Tau value is known, that is let's say 5. Now let's say I have this equation, right? From this equation g, let's say I need to know, so consider initial water level is, consider say 1 meters you can consider. So my equation becomes, this equation g becomes h of t is equal to 1 plus 2 in bracket 1 plus e to the power minus t by 5. Now I have this equation. Now by using this equation, can I find out at t equal to 10 minutes or at t equal to 10 how much will be the water level? Yes, we can substitute the value here. So for example, I will write it here 1 plus 2, 1 plus e to the power t at t equal to 10, or I need to know that after 1 second or after 1 minute or after 10 minutes how much will be the water level in the tank, right? Whether it will overflow, right? All those things I need to find out. So I will substitute here, let's say t value, say 10 divided by 5. So after solving this we will get some value. So how much will be the water level in this particular tank? That is nothing but at 10 seconds how much will be the water level that we can calculate. This is one thing or one advantage of having a mathematical model. As I told that with respect to time t, how the water level is going to change. So at 1, 2, 3, 4 minutes or at that particular second, what will be the water level that we can find out from this equation g, which we derived from the mathematical model of the plant. Second thing is that let's say I need to find out to reach 50% water in the tank. So I need to find out if h is around 0.5, there is nothing but say 50% water is required in the tank. So how much time is required for this? So same equation g we can use. Here I will write h of t. What h of t value I need? I need to know that to reach 50%. So I will rewrite this equation. So I will substitute here h of t value, that is nothing but 0.5, and I need to find out at what time t. So t is unknown in this case, so I will calculate at particular time period t. Let's say it may be 7 seconds or 8 seconds or maybe in terms of minute, the water is going to reach 50% of the tank. So once we have a mathematical model that we let's say for example, or in this case we got a transfer function model which gives the mathematical representation of a tank, and once we have this model, right, we can understand the plant behavior so that we can know how the water level is going to vary with respect to time t, or we can say how the liquid level is going to change with respect to time t. So this is the advantage of having a mathematical model. So like this we can derive a mathematical model. In this case, for this particular liquid tank, we have used mass balance principle to derive a transfer function model, and other mathematical operators like Laplace transform we used to get a transfer function model, and later in time domain, or to analyze how the process parameter like water level for this particular tank varies with respect to time t, we used inverse Laplace transform. So like this if we have a model of a plant, we can estimate how much will be the value, or what will be the process parameter value at a particular time t. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.